Equilibrium is a reversible chemical reaction in a dynamic state. So the concentration does not change because the rate of exchange is the same. So the rate forward is equal to the rate reverse. If there are 3 molecules that are going in the forward direction, there will be 3 molecules going in the reverse direction. In addition, whatever concentration you have of the products and the reactant at equilibrium, their value or their amount will not change. It will stay the same because for every molecule that is going in the forward reaction, there will be a molecule going back in the reverse direction. There are 2 types of equilibrium, physical and chemical. Physical is just a change in state of matter. So water liquid can become water gas. A chemical, there is a change in composition. So a chemical reaction is occurring, such as N2O4 becoming 2 NO2s. A reversible reaction is a chemical reaction that proceeds in both directions at the same time. Products react to produce reactants as it is being produced. If we have the following equation in which the capital letters A and B represent the reactants, capital C and D represents the products, the small letters A, B, C, D represents the coefficient of the balanced reaction, we're going to say that this equation is going to reach equilibrium, represented by this double-headed arrow. So if we graph the concentration, the reactants capital A and B will start with a large amount. My products C and D will start with almost 0 because the reaction did not begin. As the reaction starts, the reactants will decrease while the products will increase. Eventually, they will reach equilibrium. Once equilibrium is reached, the concentration of the products do not change as represented by the horizontal line. So if I extend this line back, this number stays constant. So that means the concentration of the products are not changing. In addition, the concentration of the reactants aren't changing because if I extend this horizontal line after equilibrium, that amount is the same. So the definition of equilibrium is the concentration of the products and the reactants will not change once equilibrium is reached. However, the concentration of the products and the reactants do not necessarily need to be the same. If I look at this graph, the concentration of my products are much greater than my concentration of my reactant. In a rate versus time graph, the forward rate will be greater at the beginning because there are no products produced, and the reverse rate will be low at the beginning. Eventually, their rates will be equal and opposite because when the products and reactants reach equilibrium, the rate forward is equal to the rate reverse. And how do we write the rate? We write the rate equation just like we did in the previous chapter. Rate in the forward direction is K times the reactants, and the coefficient becomes the exponent. So in this case, it'll be K1 or K4 times A brackets to the A power, B in brackets to the B power. In the reverse direction, my products become my reactants. So my K reverse or K minus 1 multiplied by C in brackets to the C power, D in brackets to the D power. So at equilibrium, if you notice, the rate is the same. The law of mass action states that the rate of the chemical reaction is directly proportional to the product of the reactant concentration values. So if I have the same equation as before, in which the capital letters are reactants and products, and the small letters are coefficient of the balance equation, we can say after a given amount of time, it will reach equilibrium. In the forward direction, K1 is the rate constant. In the reverse direction, K-1 is the rate constant. So the rate forward will equal to the rate reverse. If I write my equation, it will be K1, A in the brackets to the A, B in brackets to the B power, equals to the reverse rate, which is K minus 1 times C in brackets to the C power, D in brackets to the D power. So if I rearrange this equation, so isolating all the rate constant to one side and moving all the reactants and products to the opposite side, you get the following equation. K1 over K minus 1. This is equal to C in brackets to the C, D in brackets to the D, divided by A in brackets to the A, B in brackets to the B. This is known as the equilibrium constant. KEQ could also be K, or it could be KC. So the general formula for the equilibrium constant, according to the law of mass action, is going to be product to some power divided by the concentration of the reactants to some power. When we are writing equilibrium constant, solids and liquids are never included in the equilibrium expression because their concentration does not change. A solid concentration equals to the liquid concentration. It will always equal to 1. So we never include it. Another thing to note, equilibrium constants, whether it's for water, acid, base, solids, they are unitless. That means they do not carry a unit. However, if you solve for the concentration, you must always include proper units. When concentration for gases are given as partial pressure in units of atm, kilopascal, torus, or millimeters of mercury, this is called the equilibrium constant for gases, K subscript P. It is still product to some power X divided by reactants to some power Y. However, the units will be provided in pressure units. So if it's in pressure unit, you write your equation as Kp, partial pressure of the products to the C power, partial pressure of D to the D power, divided by partial pressure of A to the A power, partial pressure of B to the B power. However, if the concentration is given in molar, you must use Kc and not Kp, because there is an equation to convert Kc to Kp. The general Kc or KEQ is still concentration of the products to some power divided by concentration of reactants to some power. In the previous chapter, we learned PV equals nRT is the ideal gas law. Isolating P because we want the partial pressure, we divide both sides by V. N divided by V, or moles divided by V. This is the unit for concentration, molar. So substituting into the Kp, which is the partial pressure of the products to some power, divided by partial pressure of the reactant to some power. So when I substitute in for partial pressure, that is NV/RT to some power for all the product and for all the reactants. What is N over V? That is Kc, concentration in moles per liter. So what we have left over is gas constant R. Remember, R is equal to 0.08206 atm liter moles Kelvin. Temperature must be in Kelvin. And delta N is these exponents right here, which are the moles or the coefficient of the balance equation. When we multiply exponents, we add, and when we divide, we subtract. So delta N is the sum of all the moles in the product minus sum of all the moles in the reactant. So again, please note, if partial pressure is given, you are solving for Kp. If molarity is given, you are solving for Kc, because there is a conversion between Kc and Kp. This only occurs when all the substances are in the gas state. There's many types of equilibrium constant. The process to solve are very similar. So Kc, Keq are general equilibrium constant. You will also see it in the other sections. Kp is for gases, it represents partial pressure. Ka is acid dissociation constant for acids. Kb are used for bases and are known as base dissociation constant. Kw is used for water and is usually autoionization constant of water. Ksp is for solids and is the solubility product constant. However, the process to solve is the same as general equilibrium constant. Pause the video and write the equilibrium constant for the following equations, and then check your answers. General formula for equilibrium constant is K is equal to products to some power over reactants to some power. So if I look at the first equation, KEQ is equal to products. My product is going to be NaNO3 to the second power, because my coefficient is 2 here. I ignore this because that's a solid, divided by my reactants, NaI to the second power, right here, times lead nitrate in brackets. So this is my equation for A. For B, my KEQ is going to be products over reactants again. Products are hydrogen, coefficient is 2, so we have an exponent of 2, times O2 to the first power, and that's it. Because this is liquid, so we ignore it. Solids and liquids are not added into the equilibrium equation because it remains a constant. For C, KEQ, products over reactant again, we could ignore the bromine because it's liquid state. That's going to be KCl to the second power because the coefficient is 2, divided by Cl times KBr to the second power because there's a coefficient of 2. The other coefficient is 1. So for D, we're going to add all of them except for iron sulfide because that is a solid. So my KEQ is going to equal to FeSO4 in brackets times H2S divided by H2SO4. And all the powers are 1 because the coefficients are all 1 here. For E, you could do KP or KC because they're in gas state. I'm going to do Kp here. So if I write it as Kp, all of these are included because they're all in the gas state. That's going to be partial pressure of NaCl, parentheses, to the second third power, divided by Cl2 to the 1/3 power, times NO to the 2/3 power. Again, note, if partial pressure is given, you must use Kp. If concentration of the gases are given, you have to use Kc. Remember, to convert from Kp to Kc, the equation is Kp is equal to Kc RT delta N. For the following example, it says calculate the KEQ for the following if ammonia is equal to 0.0100 molar, nitrogen is equal to 0.0200 molar, and hydrogen is equal to 0.0200 molar. The concentration are given for all the gases. We need to solve for Kc. So general equation is products over reactants. So this is going to be NH3 squared divided by N2 times H2 to the cube. Now I'm going to substitute in ammonia here is equal to 0.0100 molar to the square. My N2 is 0.0200 molar, and my hydrogen is 0.0200 molar cubed, equals to 625. Since it's the equilibrium constant, it is unitless. If I work on my sig figs, this is all multiplication division. There's a decimal and a significant digit in front, so all those zeros are significant. So there's 3. Same thing here, decimal, significant digit. These 2 zeros are significant, so there's 3. And same goes here. So my final answer needs 3. 1, 2, 3. So that is correct. Pause the video, try this problem on your own, and then check your answer. So we're going to first start with the equation. So my equation is going to be Kc here. Even though these are all gas, you don't want to use Kp because molarity is provided here. Products over reactants, so it's going to be KCl squared times O2 cubed over KClO3 squared. So in this problem, we are looking for KClO3. If you're struggling with math, isolate the variable you're looking for, which is KClO3. So I'm going to multiply both sides by KClO3 squared times KClO3 squared. This cancels out. And now I need to divide both sides by Kc to get rid of Kc on the left side to have potassium chlorate by itself. So that cancels out. If I clean up the math, it's going to be KClO3 squared equals to KCl squared times O2 cubed divided by Kc. I need to take the square root of both sides, and so it becomes KClO3. I plug in. KCl is given right here as 0.00250 molar, and I need to square it. My oxygen is given as 0.05 molar, and that needs to be cubed. And then my Kc was given as 1.95 times 10 to the negative 10th. If you plug in and do all the math, you should get exactly 2. Going back and doing sig figs, there are 3 here because decimal significant digit in front of the 0, so these 3 are significant. There are 3 here. These are decimal significant digits, so these 3 are significant. And for exponents, we ignore that and count everything in front, so I need 3, so it's going to be 2.00. Since this is in concentration, we have to put units. Here it's molar. If you're struggling with the math, isolate the variable first before plugging it in. Pause the video, try this problem on your own, and then check your answer. So find the equilibrium constant for the following. We have water that dissociates into H plus and OH minus ions. So KEQ is equal to product over reactants. My reactants are H plus and OH minus. Coefficients are 1, so the exponents are 1. We do not include the water because it's in the liquid state. Liquid and solid, the concentration does not change, so it's the same thing as 1. Now I plug in. So this is going to be 1 times 10 to the negative 8 molar times 1 times 10 to the negative 6 molar. If I do the math, this is 1 times 10 to the negative 14th. There are no units because this is K. Remember, K is unitless. In addition, I want to state that a lot of times they will give you extra information that is useless. So here they gave you the concentration of water, but water is not needed. Why? Because it's in the liquid state. So read the problems carefully, especially the state of matter. Solids and liquids do not count. Gases and AQ or aqueous substance do count. Pause the video, try this problem on your own, and then check your answer. So here we have 4 moles of SO2, 5 moles of O2 in a 2-liter container at 100 degrees at equilibrium. Calculate the equilibrium concentration of SO3 and the number of moles of SO3 present if equilibrium constant is given. If I look at my equation, they're all gas states. However, the units that are given is molarity because moles and liters are given, so we are solving for Kc. So my Kc equation is going to be products over reactants, and this is going to be SO2 squared because the coefficient is 2 times O2 divided by SO3 squared. We are looking for SO3, so you could rearrange the problem. You could rearrange to isolate the variable. So if you do that, you should get SO3 squared is equal to SO2 squared times O2 divided by Kc. And remember, we have to take the square root. So now I'm going to plug in. So that means SO3 is going to equal to the square root of SO2. So SO2, we have moles that are given and the liters. So we have to solve for concentration. Remember, concentration is moles per liter. So for SO2, my concentration will be 4 moles divided by 2 liters squared. And for oxygen, there's 5 moles in 2 liters. That's going to be 5.0 moles in 2 liters divided by the Kc, which is provided as 1.47 times 10 to the negative 3rd. Solving for the math, 82.4786. There are 3 here because there's decimal significant digits, so those zeros are significant. For 2.0, there are 2 significant digits because there's decimal significant digits, so that 0 is significant. For the 5, there is also 3 because there's the decimal significant digit. and 2.0 already has 2, you know, and then my constant has 3, and I would not really count the constant because it is a constant. So least amount is 2, so 1, 2, I look 1 to the right, so it's 82. Since this is concentration, you must have units of molar or it's incorrect. They also want you to find the number of moles of SO2. You could do that. There are 2 ways you could solve for this. You could do molarity is equal to moles per volume, and if I do that, I multiply both sides by volume. So this becomes moles is equal to volume times molarity. So if I use that, that's going to be 2.0 liter because that was the volume given, times 82 moles, which equals to 164 moles. If we do sig figs, there will only be 2, so 1, 2, so this is going to equal to 1 moles. Or you could use dimensional analysis. There are 2.0 liters and there's 1 liter to 82 moles. Remember, when we have 82 molars, that's the same thing as saying there's 82 moles per 1 liter of solution. So it becomes a conversion factor. KEQ is equilibrium constant. It is always products over reactants. We do not include solids and liquids because their concentration does not change. Gases are given and partial pressure is given, you use Kp. If concentration is given, you use Kc and then convert it to Kp.